Welcome to this explainer. I am your lead strategist, and today we are stepping into the shoes of physics paleontologists. What does that mean? It means we are digging deep through the fossil layers of Cambridge past paper questions to reconstruct the absolute ultimate foolproof exam strategy for gravitational fields. Now, if you have ever stared blankly at a past paper and felt totally overwhelmed by the tangled mix of uniform fields, radial fields, and those incredibly frustrating negative potentials, you are in exactly the right place. We are going to break this entire topic down logically, layer by excavated layer. But we're not just looking at the physics facts today, we are looking at how to actually score the marks. I see two types of students every single year. Let's call them Alex and Sam. Alex is the overloader. Alex will dump every single raw physics fact they have ever memorized onto the page, completely ignoring the analysis the examiner actually asked for. And then there's Sam. Sam rushes. Sam completely misses the specific command words in the question, drops crucial details, and loses easy marks. Today, we are going to fix both of those approaches. Whether you are tackling Syllabus 9702 or building foundations in 0625, 0652, 0654, 0972, or 5054, these strategies are going to completely transform your answers from red ink to green check marks. So let's grab our tools and dive right into this.
To truly master this topic and secure those top-tier grades, we are going to journey from the Earth's surface outward into the vast cosmos. We will progress through 5 distinct stages: the ground layer of forces, point masses and spheres, the complexities of orbital mechanics, the mind-bending concept of infinity, and finally gravitational potential energy.
Section 1. The ground layer. This is where we look at forces and fields right under our feet.
Okay, let's start at the surface with the foundational concepts you already experience every single day of your life. As you can see brilliantly illustrated here, near the Earth's surface, the lines of gravitational force are extremely near to being perfectly parallel, and they are equally spaced. In the language of physics examiners, when field lines look exactly like this, it means the gravitational field is essentially uniform. If you drop a pen, it falls straight down with a constant acceleration, regardless of whether you drop it from your desk or toss it out of a second-story window. The force it experiences is constant because the field is uniform. Now, if the exam asks you to describe this, don't be like Sam and just write gravity goes down. You need to hit the assessment objectives. Use the Peel framework. Point, the field is uniform. Evidence, the field lines are parallel and equally spaced. Explanation, this means the force exerted on a mass is constant at any point. Link, therefore, the acceleration of free fall is constant near the surface. Boom, full marks.
The definition of gravitational field strength is absolutely crucial here, and you have to get the wording perfect. It is the gravitational force per unit mass at a specific point, measured in newtons per kilogram. If the command word is defined, you write exactly that. But here is the profound conceptual point that ties it all together. If you compare Newton's second law, F equals ma, with the weight equation, F equals mg, you realize something so fundamental it's almost beautiful. The acceleration due to gravity and the gravitational field strength are exactly the same thing. Mathematically, they are identical. They are literally just two different ways of looking at g.
Section 2. Point masses and spheres. What happens when we leave the surface? As we move slightly away from the surface of the Earth, we have to completely rethink how we calculate the attraction between finite objects. Notice the radial pattern of the field lines shown here. For a uniform sphere like a massive planet or a burning star, trying to calculate the pull from every single atom would be a mathematical nightmare. But thankfully, there is a brilliant rule that simplifies everything for us. All the mass of a uniform sphere can be considered to act at a single, solitary, central point, its center of mass. Because of this, the field becomes radial. It spreads out in all directions from the center, rather than being uniform and parallel like it is up close on the surface. And hey, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look at how examiners test this radial concept.
This right here is a classic exam blueprint. This is where the transformation happens from an average paper to a top-tier paper. You will very frequently be asked to derive the formula for the field strength of a point mass. Don't panic, just follow the steps. Step 1. Recognize and write down Newton's law of gravitation, which states the force F equals big G times mass 1 times mass 2 all over the distance squared. Step 2. Combine that with our earlier definition of field strength, little g equals force over mass. Step 3. The small test mass m beautifully cancels out. You arrive at the vital equation, little g equals big G times big M divided by r squared. When Alex gets this question, they'll write a massive paragraph about Isaac Newton sitting under an apple tree. 0 marks. All the examiner wants to see are these 3 clean, logical, mathematical steps.
Now, let's do a quick visual workshop. I want you to look at this graph. Imagine a 60-second timer on your screen right now. Scan the data. What is the core trend? Notice how the curve drops off incredibly sharply. This visualizes the infamous inverse square relationship. Because our distance r is squared in the denominator of our new formula, if you double your distance from the center of the planet, the gravitational field strength doesn't just cut in half. No, it decreases by a factor of 4. If you triple the distance, it drops by a factor of 9. The lines of force get further apart very quickly as you move out into the emptiness of space.
Section 3. The orbital layer. Mechanics. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Let's blast off!
Welcome to the orbital layer, where satellites and space stations reside. To solve circular orbit problems, you absolutely do not need to memorize 100 different complex formulas. Let's do a 30-second speed writing challenge in our heads. You simply dust off your circular motion equations and set them exactly equal to Newton's law of gravitation. Why? Because the gravitational pull is literally providing the centripetal force. It's the invisible string keeping the satellite spinning. So, step 1, you set mv²/r equal to big G, big M, little m over r squared. Step 2, the mass of the satellite, little m, cancels out on both sides. One of the distance r's cancels out. Step 3, you are left with the exact orbital speed required to maintain that orbit. Velocity v equals the square root of big G times big M over r. Perfect PL paragraph logic right there in mathematical form.
Physics is so beautifully interconnected. Since linear speed v can also be expressed as angular speed omega times the radius r, we can expand this entire concept to determine the exact time, or period, it takes for a satellite to complete one full orbit around the Earth. By manipulating these core equations, space agencies can confidently place a multi-million-dollar satellite at the exact height needed for any specific mission.
And speaking of specific missions, let's play Find the Flaw. If a question asks about a geostationary satellite and Sam writes, it's a satellite that stays in space for 24 hours. Where are the lost marks? The flaw is that it lacks precision. 24 is indeed the magic number. 24 hours is the exact orbital period required for a geostationary satellite. But to get the marks, you must specify that it is placed directly above the equator, orbiting from west to east with a period of exactly 24 hours. Because it matches the Earth's rotation perfectly, it will appear to hover permanently over the exact same point on the ground. That is the complete, high-grade answer examiners are hunting for.
Section 4. The concept of infinity. Let's push our understanding out to the absolute infinite limit.
This layer contains arguably the most counterintuitive rule in the entire Cambridge syllabus. The crucial point to grasp here is how physicists define zero. Exactly zero gravitational potential energy is defined as being at an infinite distance away from a mass. Why? Because at infinity, the gravitational pull is practically non-existent. It's zero. But think about what happens as an asteroid falls from infinity towards Earth. As it falls, it speeds up, gaining a massive amount of kinetic energy. By the fundamental law of conservation of energy, if it's gaining kinetic, it must be losing gravitational potential energy. So if it starts its journey at zero and loses energy all the way down, its potential energy must dip into the negative numbers. Therefore, anywhere near a planet, gravitational potential energy is a negative value.
This brings us to a definition you absolutely must lock into your memory: gravitational potential, represented by the Greek letter phi. If the command word is define, you write the work done per unit mass and bringing a small test mass from infinity to that point. Notice it says work done per unit mass. This is incredibly important. It is a property of the gravitational field itself at a specific location, totally independent of whatever small object you might eventually decide to place there. Because we start at zero at infinity and lose energy coming inward, the gravitational potential at the surface of any object in the universe is always negative.
Look at this potential well diagram on the screen. It is a brilliant visual translation of that concept.
It perfectly shows how the lowest, most negative potential point is right at the solid surface of the planet, marked as radius r. As you move outward, extending your distance r towards infinity, the curve slowly rises. It gets less and less negative, eventually flattening out as it approaches that zero line at infinity. It is quite literally a mathematical hole, a well, that an object has to spend energy to climb out of to escape a planet's gravity.
Section 5. Gravitational potential energy. Let's connect our conceptual potential back to actual physical energy. Remember, gravitational potential, our phi, is just the energy per unit mass. So to find the total real gravitational potential energy of a physical object, you simply multiply the potential of the field by the actual mass of your object. This gives us our final major equation. Energy potential equals negative big G, big M, little m, all divided by r. Take a really close look at that denominator. It is over r, it is not over r squared. Sam always puts r squared here because they confuse it with the force equation, and they lose the mark every single time.
And speaking of losing marks, I want to highlight a massive exam trap that catches out thousands of students globally. When we consider a tiny, small meteorite orbiting a massive planet, our human brains naturally think the meteorite has the potential energy because it's the thing moving. But remember Newton's third law. The concept of equal and opposite interactions applies to energy systems too. It's a shared system. The massive planet also has the exact same magnitude of gravitational potential energy due to the tiny meteorite's presence. The energy belongs to the complete system of the two masses, not just the small one. If the exam asks you to explain the energy of the system, you must mention both bodies.
Okay, my fellow physicists, screenshot this revision cheat sheet right now. Let's talk about the final system that guarantees top marks. First, command word decoding. Know the difference between define, derive, and explain. Second, Peel framework application. Point, evidence, explanation, link. Don't just list facts like Alex. Third, the time management matrix. Spend your time on the high-mark derivation questions, not over-explaining one-mark definitions. Now look at these 4 essential equations. Notice the patterns. The top 2, field strength and potential, only have one mass, big M. They describe the invisible field itself. The bottom 2, force and potential energy, have both masses, big M and little m. They describe the physical interaction between two actual objects. Also check the denominators. Force and field strength are over r squared. Energy and potential are just over r. Memorize this grid, apply the 3 rules, and you are golden.
As we wrap up this explainer, I'm going to leave you to ponder this vital exam question. Why was infinity chosen as the zero of potential rather than the surface of the Earth? Think about it. If we use the Earth's surface as our zero baseline, what happens when we travel to Mars or Jupiter? Every single planet would require a completely different mathematical baseline. By choosing infinity, the blank, empty canvas of deep space where there is zero gravitational influence, the math becomes infinitely more elegant and universally applicable across the entire cosmos. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep asking why as you study, and I'll see you in the next one.